Welcome to the integrated rate law. So, thus far, the rate laws that we've looked at have been differential rate laws. So the differential rate law tells us the rate as a function of the concentrations of our reactants. But sometimes we want to know the concentrations of our reactants as a function of time. So for this, we need an integrated rate law. So let's look at some generic first order reaction. So we have some reactant A is reacting to form some products. One product B or some combination of products B and C, doesn't matter. Note that the lowercase a here represents how many moles of uppercase A we are decomposing. So the lowercase a is our coefficient, the uppercase A is the identity of our species, whatever it happens to be. So our differential rate law then is the rate is equal to our rate constant K times the concentration of species A to the first power. We know that that power is 1 because we've specified that it's a first order reaction. It's first order overall. There is only one reactant, so we know that the power on our concentration of A then is 1. So if we use calculus to integrate the differential rate law for our first order reaction, then we get this. I'm not going to go through the derivation of this, but then we get our integrated rate law, which is the natural log of the quantity, A naught divided by the concentration of A naught. So this is the concentration of A at time 0 divided by the concentration of A at time t, whatever time we're interested in looking at, is equal to Kt, where K again is our rate constant, T is the time. So if we plot then the natural log of A versus time for a first order reaction, we get a straight line, so we get something like this. Note that if we just plot the concentration versus time, we get a curve. But if we plot the natural log of concentration versus time, we get a straight line. And in this case, the slope of this line is equal to negative K. Remember, K there is our rate constant, so this is the opposite of our rate constant. Note that we have a negative slope for reactants or a positive slope for products because, again, the concentration versus time curve for our products would look something like this. And so then for the natural log of that red curve there, we'll get a straight line that's supposed to be straight with a positive slope. So now let's look at half-life. So half-life of a reactant, which we symbolize here as T1/2. This is the time required for a reactant to reach half of its original concentration. And by definition, the concentration of the reactant A at the half-life is equal to the initial concentration divided by 2. It's half the initial concentration. So at the half-life, T1/2, we know that this concentration, how much we have left, is half as much as what we started with, the A naught there. So for a first order reaction then, we have our integrated rate law. And we know that at our half-life time, at T1/2, we know that our concentration, so our concentration of A at that time, is half of what we initially had. And now that fraction inside the natural log, inside those parentheses, simplifies to 2, because here we're dividing our initial concentration by our initial concentration divided by 2. So the result there is 2. So we have the natural log of 2 is equal to K, the rate constant, times our half-life, T1/2. And now if we solve that for our half-life, we get T1/2 is equal to the natural log of 2 divided by K. Well, the natural log of 2 is 0.693. And so we have that our half-life is equal to 0.693 divided by K if our reaction is first order. So note that our half-life doesn't depend on the initial concentration of A for our first order reaction, right? Because the only thing in here is this natural log of 2, that's a constant, and this value of k, our rate constant. So the half-life only depends on what our rate constant is. Now the rate constant may depend on things like the temperature, perhaps the pressure, maybe, but it doesn't depend on the concentration of our reactant. So this means that for a first-order reaction, if we know what the value of k is, we can figure out what the half-life is, and that means that it doesn't matter how much you start with initially, at that half-life, let's say it's 1 minute, after 1 minute, you have half as much around. And then after another minute, you have half as much of that around, and after another minute, you have half as much of that around. And so every minute, you have half as much. So after the first minute, you have half as much of what you started. After the second minute, you have a quarter as much as what you started. After the third minute, you have 1/8 as much as what you started with, and so on. So for some generic second-order reaction, so again, I could have written a second-order reaction as A plus B, but in this case, it's easier for me to show it this way, with A being a second order instead of A being first order and B being second order. So we have our coefficient of lowercase a, and uppercase A again identifies what our species is. It's reacting to form some product. So our differential rate law there is rate is equal to k, the rate constant, times the concentration of A squared. Again, it doesn't matter what this coefficient, what the lowercase a is, right? That lowercase a doesn't have to be a 2. It might be, it might not be. So here we have our differential rate law for our second order reaction. And if we integrate this, again, I'm not going to go through the derivation, but now we get the inverse, so 1 over the concentration of A at time t, the time that we're interested in, is equal to k, our rate constant, times t, plus 1 over A naught, concentration of A at the beginning, before we started. And then the half-life is then given by this equation. So T1 half is equal to 1 over K times the concentration of A initially, our initial concentration of A. So note that our half-life now depends on the initial concentration of A for our second order reaction. Also note that as our concentration of A, as our initial concentration gets larger, the value of our denominator gets larger, which means the value of our fraction gets smaller. And that means that our half-life is getting smaller. So for a second order reaction, the more stuff we have initially, the more of our reactant we have around, the faster it's going to proceed, which means that the faster we will reach our half-life, the shorter our half-life becomes. And as time progresses, as we react away our reactant, our half-life will get longer and longer and longer because our concentration gets smaller and smaller and smaller. So a plot of the inverse of A versus time will be linear for a second order reaction. So this means that our slope will be positive. So again here we have our concentration versus time curve. Here the purple curve is our second order reaction, that's the top curve. And the pink curve, the bottom one, is a first order reaction. So note that initially the second order reaction will probably occur faster, but then over time, second order reaction slows down faster than the first order reaction does, and thus it comes to equilibrium faster. The first order reaction is still proceeding by the time it cuts off there. So note that then here we're only plotting the top curve, the top reaction, our second order reaction here. If now we still leave time as our bottom axis, but now on the vertical axis, the y-axis, we have the inverse of concentration. So we're plotting 1 over concentration of A at each time. So down here, the intercept is 1 over our initial concentration, because again, we're at time equals 0. And that means that as time proceeds, our value, our inverse gets larger. Now remember, this is occurring because our concentration is getting smaller, but as we take the inverse of our concentration, our value will be getting larger with time. And the slope in this case is equal to K, our rate constant. Okay, so we've looked at first order reaction and second order reaction, so now let's look at a zero order reaction. So, again, we have our generic reaction, A, lowercase a, numbers of molecules of uppercase A species, react to give us some products. Our differential rate law in this case is rate is equal to our rate constant K times the initial concentration. The concentration of A to the 0th power. Well, anything to the 0th power is 1. So that means that our rate is equal to K times 1. So that's what I've written here, which means that the rate is equal to K. Now, that means that the rate depends on the value of our rate constant, but it doesn't depend on the value of the concentration of A. So now, for a zero order reaction, it's going to proceed at some rate regardless of how much A we have around, which seems a little weird because now this is the only reactant involved, but it doesn't matter how much of that we have around. As long as we have some, the reaction is going to proceed at a set rate. That set rate is given to us by K, value of our rate constant. So, if we integrate and get our integrated rate law, again, I'm not going through the derivation, we get the concentration of A at some time t is equal to negative KT plus our initial concentration of A. So, this means that the half-life is then given by this equation, so T1 half, half-life is equal to our initial concentration of A naught, divided by 2 times the value of our rate constant K. So, note that our half-life now does depend on the initial concentration of A for a zero order reaction. But this is because the rate doesn't depend on the concentration of A. And so, in order for us to get to decompose half of our A, we have our initial concentration of A divided by 2. That's how much we need to get rid of. Well, we're getting rid of K amount every second or every period of time. So we divide that value by K, and that's the half-life that we have. So, in this case, a plot of concentration of A versus time will be linear. So if we plot concentration versus time, we get a straight line. It will decrease until we have no more of a reactant present, and then it will just be a flat line at 0 because we have no left. So again, our plot will be linear for a zero order reaction. Our slope will be negative for a reactant, positive for our product, and our slope will be equal to K. So in the Zumdahl text, you can look at table 12.6 for a summary of properties of the zero first and second order reactions. That's this table here. So that was the integrated rate law.